So we started Gaussian elimination last time, and that's a procedure that gives us a way to solve linear systems. And we worked through a couple of problems by hand, simply because we need to know how the procedure works before we can program it. And for programming it, so when we are just looking at the problem, we can kind of feel it out which coefficients to use to basically, in a system like this is my general augmented matrix. So if we are solving A times X, in this case X has 3 unknowns, it's a vector of 3 unknowns, is equal to B, B is my right-hand side, then the procedure, Gaussian elimination, starts with eliminating positions in matrix A under the diagonal, with the objective of creating the upper triangular matrix. Now, or sometimes also called row echelon form. Now, I can do that in various ways. What's always allowed to do without changing, so our objective is to find the solution to the system. If I multiply one of the equations, which is a row in this augmented form, by some non-zero number, I haven't changed the solution. I can also do a linear combination of 2 rows and replace one of those rows with that linear combination. I still haven't changed the solution. So I can do transformations like that without changing the solution. So we are basically transforming this system into something that is easier to solve without changing the solution that we are looking for. So that is the idea of Gaussian elimination. So if I was going to generalize this and basically take this A here and I want to make it a 0. So in most general case, what we'll want to do is find the coefficient, and I call that coefficient C2, that I can multiply first row with, and in particular when I'm multiplying first row and adding it to the second row, I will basically have C2 times this row 1 plus R2, and in this position in the first column, I'm going to have C2 A11 plus A21 has to be equal to 0. So if I look for the coefficient, it's simply a negative this divided by this. So we call this first element here pivot element, and I'm using that pivot element to eliminate all of the elements below it. Okay? So once I'm done with the first column, so I can proceed and do that here as well. Now my coefficient will change to A31 divided by A11, negative version of it. So basically I can multiply this row with this coefficient and add it to the third row and replace that third row with that. Okay? And if I had a longer, bigger matrix, I just keep going to the end of that column. Right? And after that, I will switch to this pivot element, which is in the second row. And I'll just keep going until I'm actually done with the matrix. So do we see sort of like mentally an algorithm of how it works? So our objective will be to program this to work with any size of matrix. This is where I'm going to leave you a choice. I still have some examples that we can do by hand, or we can start programming. Do you feel like programming this Friday? Yes? All right. So then basically, this is what I want to do, right? So I want to take in a matrix, and let's do first this first part of Gaussian elimination, that is creating zeros below diagonal. So let's just simply open up and start Anaconda. And I'm going to grab one of the examples. So we're going to work this on an example. an example that we solved by hand. So we're gonna basically work with that example first, okay? Though we're gonna attempt to be general and just size up the matrix as if we didn't know about how big it is. And then we're gonna try to package that into a function that will work for any matrix that I designed. So that's, if you figured out by now, that's a good way to proceed. You start with a small example, you kind of work out step by step to see that you essentially understand. And then you can kind of package that into a function that you can use in a more general case. But that way, we also test it at the same time. So let me just get to my lectures, there we go. And Spring. So I'm just gonna start a new one. So I'm gonna say Lecture 6, solving linear systems, Gaussian elimination. Okay. So I'll first gonna type myself an example. Small system. I need matrices, I need vectors. I better import NumPy as NP. And I'm going to type in the example. There's that matrix A that was -3, 2, -1, 6, -6, 7, 3, -4, 4. So basically my example system is -3x1 plus 2x2 minus x3 equals to -1. And then 6x1 minus 6x2 plus 7x3 is equal to -7, and 3x1 minus 4x2 plus 4x3 is equal to -6. This was the example that we solved by hand. A little bit of spacing here. So my first task number one or task one is create matrix A and vector B corresponding to this system. And then after that, use nested loops to, or let's do first task is simply eliminate all elements in A that are below position. In Python, it's 0, 0, like that very first element. So that's my pivot element. So we're just going to work on that first column. So let's just do that as a first task, and then we're going to proceed with other pivot elements. Okay? So how about you work on that, and Ningyu and I will walk around a little. And just don't forget to do not forget to modify elements of B. So this is called forward elimination on the first column of A. So just as I was doing things by hand, I would kind of work on those two lines. And if you need to refer to your notes from the way we were doing it by hand, you can. But I want you to think about a little more general sense of how to do that. There are no questions. I'm going to type in A. Choices this Friday. Which choice would you like? Your task is written for you. Has anyone successfully eliminated or modified the second row? Or row 1 using row 0? How do I actually, first question. If I wanted to print first row of A, what would I, or the 0th row of A, what would I do? Right? It's my, right? So that's 3, 2 minus 1, that's correct, right? If I wanted to do something with it, I could multiply that row 3 times A, right? Plus 2 times A of 1. Okay? This is my linear combination of the row 0 and row 1, right? 3 times row 0 plus 2 times row 1. Yes? This is apparently what I get. I shouldn't forget to actually work with B as well, so my parallel processing of B would be 3 times B of 0 plus 2 times B of 1. Okay. Okay. So I can do these things, and I can also replace an entire row of A with something like that. Okay. So this is how I would actually program whatever we were actually doing by hand. We were replacing an entire row with a linear combination of the other 2 rows. So this is printing, calculating linear combinations of row 0 and row 1. Okay, so I have all of my little elements of how to get things and what to do with them. So now if my I'm gonna call this first row, I'm gonna work with it as a 0, I is equal to 0, so I'm gonna call it I, so I can be a little more, and I'm gonna call my row 1 J, or maybe K, or some, it doesn't matter, whatever I call it. So now if I want to replace my row 1, my row J, in this case, with the linear combination of row 0 and row 1, how would I type that in? So if I want to replace, so this is a linear combination, right? So let's say that I want to replace row 1 of A with that linear combination, whether it's a good one or not. What do I write down?
So can we call that function name and then substitute that into...
So this is what I want to replace who? Can I do this? This is, it's possible. If not, I go line by line, but let's give it a try, okay? And then I'm going to print it. Okay. So I have replaced my second row with this calculation, whatever it is, right? Except that's not the correct linear combination to eliminate my 0, yeah? So now we just have to figure out, well, which linear combination. And I say, so this is, and I'm going to call it J, and this is going to be I, it's going to be J, okay? I just have to figure out what coefficients do I use. So there was that magical coefficient that I called C, right? That I want to multiply this 0th row and add it to the second one to get a 0 in that position. And in those notes that I had, that C was, well, here I started with A11, should have with A00 to be more Python-y. But basically, it's my C is this element of A divided by this element of A, negative version of it. Do we agree? Because that should work mathematically, and that gives me a system that I can work as a program. Let's give it a try and see whether it works. So now I say, hey, C should be equal to minus A of J 0, right? Divided by A I0. And I'll recognize that I'm calling 0 I, so I'm just going to replace it with I. Let's see whether that works. If it does, I can print entire A actually. Okay. If it does, I should have a 0 just below my first, the 0, 0 element in A. Boom. I have 0 here. So what I did now is I just really typed in what we were doing by hand, and it was so easy by hand, and you're like now looking at like, really, is this supposed to make it easier or something? It's supposed to make it easier once you actually have A that is 100 by 100, when you don't want to do it by hand. Everybody cool with this? Well, problem is also I didn't change B, so let me do that. My B of J on that right-hand side should actually go and be modified the same. C times B of I plus B of J. And that doesn't have to be 0, it's just what it is. So that's great. And now technically, I can do this just for also the row 2. So now I'm just going to go call J2, which was the whole point of me calling it something else so I can easily replace. And that should just work for that last row. Oop, boom. All I did is just cut, copy, paste, and I replaced J with 2. So if I had more larger A, I would keep going until I have rows of A. Does this call for a loop? Yeah? It does. So I'm going to leave this here. I'm going to copy everything and create a loop out of it. So this is the step-by-step. First, type in as if you were a calculator and you were just replacing what you're doing by hand. And try to generalize a little. Is everybody clear with this before I move on? So this is basically a linear combination of my row 0 and row 1. This is, in this case, linear combination of row 0 and row 2. And I just kind of used I and J so I can do this smart little change. That's the whole point when you're writing code. Everybody cool? Everybody got here? Questions? So,
Oh, great. So if you got here, create a loop out of this. Just copy the entire thing. Just like step by step improve your code. So just let's do a loop for j in which range? To get 1 and 2, what is the range? One comma. I think I heard 3, or maybe I just wanted to hear 3. Okay, I didn't make any mistakes in creating the loop. But my code is way cleaner now. Now, what is 3? 3, the matrix 3 is 2. It is Friday. We're getting philosophical. I'm pretty sure we can find a dimension or geometry where 3 is 2. But we're going to stick with the one we have. So this is a 3 by 3 matrix. So it's essentially 3 is the size of the problem. I go until I have elements of A. So I'm going to generalize this on the spot. Okay, I'm going to say this is n and n, comma, n, or should be my A shape. That should work. If not, I'm going to call it M. There we go. So again, I'm thinking how to generalize this because ultimately I want this to work for a matrix that is 20 by 20. So I've done it for the first row. This A could be larger, okay? And this elimination would still work. Now I want to also, we know that after we were done with the first column, we switched to the second column, but we were working with that element that was also in the second row. If you want to talk Python speak, we switched from column 0 to column 1. And my pivot element is now the diagonal element, which is 1, 1, right? And then I move over. In a 3 by 3, there's not much to do afterwards, but right? But if I had a larger system, I would keep going, okay, until I have diagonal elements, right? So technically, this I is a loop as well. Yes? Can you write down a loop that would now actually do everything, but also loop for all of the I's that are relevant? And my J has to kind of switch with respect to I, right? So if it helps, if I was working with the second, how would you modify this code to actually work with I is equal to 1 now? Does everything stay the same? This has to change. So it's actually related to I. It's next one after I. Yes? Next one below I. So this is actually, it's 2, if you will. Or technically, I plus 1. Yes? So now nest this in an I loop to do a complete forward elimination of.
Why do we flip for J in range instead of for I? Why do we flip for J in range for the second one instead?
So this is, let me just write down notes. So working on eliminating elements below A1. So this is my row 1. So your task now is task 2, generalize elimination so it works with all columns of A. Mm-hmm.
So we flip for J in range of I plus 1 instead of for I in range because we're gonna.
Right, so what is my range of i's? So I want to actually, I don't want to write here row 0 and then write I is equal to 0, then copy the code for I is equal to 0. Then I have I is equal to 1, then I copy the code for I is equal to. That's what another for loop should be for. So I need a for loop for I, right? That will work about this. So I will have a nested loop. If I'm traversing a matrix, I should always have a nested loop, right?
That's what I was asking. So if it's a loop right, why do we write J?
I need both. Okay? Above loop for J, I need a loop for I, so that I don't have to cut, copy, paste for every I. Yes? Do that. And you can in stages copy entire code in the next cell and work with that so that you have all of the stages kind of done. Or actually, I'm just going to repeat I.
Is it okay if we put I on it?
Oh, oops. Something's not okay. Uh-uh. Double scalar. Okay. Ah. This is the problem. I did not copy the correct one. That's better. I had that one left over. I didn't. Correct. So I have 0, 0, 0. At least on this 3 by 3 example, it seems to have worked. Just forward elimination. Done for this matrix. And really, it seems that it is general. I take the size of the matrix, right? I'm working for basically all i's from 0 to n minus 1. That last one is actually really not going to happen because the last my diagonal element, there's no j under it, but it's still correct to write it that way. It's just not going to, nothing will execute for that very last diagonal element. Now I'm not doing any checks whatsoever. Is matrix square? Is this, I'm dividing here by a of a of II. It could be 0. This could be true. So if I need that partial pivoting business, so what I'm going to do here is say if a of II is different, like its absolute value of it is larger than 0, then do this. Otherwise, print, please program partial pivoting. So for now, I give myself a warning. I have some work to do. Hint, hint, this work will be your homework to modify this code to do partial pivoting. The perfect little thing to spend your weekend on. I hear it's going to be raining this weekend. Maybe we should assign homework immediately today, not wait for Monday, because rainy weekend increases productivity of students because there's nothing to do outside. I'm not kidding. There is research showing that in places where the weather is more miserable, people are generally more productive. Or on days like, you don't want to be outside. Let's stay inside and work. There's like more trading on the international scenes going on days. Like there's all kinds of proofs. If it's sunny and pretty, why code? So I'm just gonna throw myself a warning that I should not divide by 0, and I will avoid dividing by 0, so it's basically nothing will happen here. Okay, cool. So that's my forward elimination. What did we say? What do we do after forward elimination? So I have now my B could be a column. It doesn't really matter that my B is column as far as Python is concerned. So what's my last element, in this last row, how do I solve it?
Put it back into the system.
So my minus 2x3 in Python speak x of 2 is equal to 2, right? So I start from that last element, and I can first type it in as a calculator, and then after that I can figure out a nice little for loop that will go backwards, right? And give me the solution. And that's what we're gonna do on Monday. Yes? So so you gotta know how to solve things by hand. You have to generalize it because when you're solving by hand, you're using your intuitive self. Computer is not intuitive, tell it precisely what to do. And we want to create loops that will just loop through the entire problem. See you on Monday.